If you follow energy news at all, you've probably experienced this exact kind of whiplash.
Oh, absolutely. I mean, it's basically a daily occurrence at this point.
Right. Like on Monday, you'll read this headline declaring that solar power is now, officially the cheapest energy source in human history.
Yeah, and then Tuesday rolls around.
Exactly. Tuesday, you see a completely different report warning that the grid upgrades required to support all that solar will end up costing taxpayers trillions of dollars.
And it just leaves you sitting there wondering who is actually telling the truth.
Right. Like, are renewables this miraculous financial bargain, or are they just a hidden black hole for our infrastructure budgets?
Well, it really is the defining paradox of the entire energy transition debate right now. I mean, we see politicians and economists constantly throwing around the word cheapest,
Yeah.
but we rarely stop to actually define what cheapest means when a power plant has to interface with the incredibly complex reality of a national electrical grid.
And that is exactly our mission for today's deep dive.
Yeah.
We are going to decode the true hidden price tag of our energy future.
It's a big undertaking.
It is, but we're going to figure out how we can fairly compare vastly different energy sources. Like a massive offshore wind farm versus a decentralized rooftop solar array
Yeah.
versus a traditional nuclear power plant.
Right.
And to do this, we're unpacking a really fascinating piece of research. The full title of the source material we're exploring today is SLCOE, System-Based LCOE, for comparing energy technologies in different systems.
Which is honestly a massive paradigm shift in how we look at this stuff.
Yeah, how so?
Well, this study essentially argues that the standard metric the entire world has used for decades, to compare energy costs, is just fundamentally broken.
Wow, broken.
Yeah, I mean, it's no longer fit for purpose in a modern decarbonizing world. So the authors are proposing a completely new lens to view, not just the cost of a power plant, but the cost of the entire society surrounding it.
Okay, so let's set the stage here. You probably already know the standard metric everyone argues over. It's called LCOE, right? Levelized cost of energy.
Exactly.
It's the traditional way of calculating the long-term marginal cost of producing one single unit of energy. Usually it's expressed in like dollars or euros per megawatt hour.
Right, and the formula is pretty straightforward on paper. You take the initial investment, you add the operation and maintenance.
Factor in the fuel costs over the lifetime.
Yeah, and then you just divide all of that by the total amount of energy it will produce, and it spits out this clean, simple dollar amount.
But the problem with the clean, simple dollar amount is that it creates a massive blind spot, doesn't it?
A huge blind spot. Because LCOE treats a highly predictable, constant energy source, like, say, a coal plant, exactly the same as a weather-dependent variable source like a wind turbine.
Right.
It completely ignores what this study calls flexibility constraints.
Okay, let's unpack this. Because comparing energy sources using LCOE is basically like comparing the cost of buying a printer without ever looking at how much the ink cartridges cost.
Oh, that's a great way to look at it.
Or, checking if it even connects to your Wi-Fi. You just see the sticker price on the box and think, wow, what a steal.
Right, but that sticker price ignores the reality of actually integrating it into your specific home often.
Exactly. You bring it home and realize, oh, I have to buy special cables, I need a specific operating system, and the ink is going to bankrupt me. Those are the system costs.
Yeah, LCOE entirely ignores the thousands of dollars in upgrades required just to turn the machine on safely. It's only a function of the technology itself.
Just lives in a vacuum.
Totally. It assumes the grid is this infinite, perfect sponge that can just absorb electricity at any moment from any source without any friction at all.
Which is definitely not how the grid works.
No, not at all. The real-world grid doesn't care about the weather. It needs power in the exact millisecond you hit your light switch. So if you only look at the LCOE of, say, a solar panel, you are completely ignoring the cost of the massive chemical batteries needed to store that power for the evening.
Or the cost of the backup gas plants just sitting idle waiting for a cloudy day.
Exactly. Which brings us to the core concept the study proposes, which is SLCOE. System-based levelized cost of energy.
And this shift in the formula changes everything.
It really does, because while traditional LCOE evaluates the isolated technology, SLCOE evaluates the technology combined with the specific energy system context it operates within.
So you take the baseline LCOE and you add the system integration costs required to make it actually useful to society.
Right. What's fascinating here is that a single offshore wind turbine actually has a completely different financial price tag depending on the specific grid you plug it into.
Okay, wait, explain that. How does the same turbine cost different amounts?
Well, if you drop that wind turbine into a rigid, outdated system that just cannot handle its unpredictable surges and lulls in power.
Like today's grid?
Yeah, exactly. The system costs, the backups, the batteries, the grid reinforcements, they skyrocket. So the SLCOE becomes massive.
Okay.
But if you plug that exact same turbine into a highly intelligent, flexible system designed to seamlessly absorb variability, the system costs just plummet. The machine itself hasn't changed at all. The environment dictates its value.
That makes so much sense. So to prove this, the researchers obviously couldn't just do some back-of-the-napkin math. They needed a highly detailed testing ground, which leads us to their methodology.
Right, and they used Denmark as a highly detailed case study for this.
Because Denmark maintains incredibly granular modeling of its entire national energy infrastructure, right?
Exactly. They utilized this sophisticated modeling tool called Energy Plan. And they didn't just look at annual averages, which a lot of studies do. They ran an hourly simulation for a full year.
Wow, so that's, what, 8,760 individual hours where supply has to perfectly match demand.
Yes. So if the wind stops blowing on a cold Tuesday night in February, the model has to figure out in that exact hour where the replacement power is coming from.
And calculate the financial cost of that specific balancing act.
Pretty nicely. And to see how different environments affect the SLCOE, they basically simulated two completely different arenas.
Let's talk about those two arenas. The first is what they call the electricity-only system. And this basically represents today's reality, right?
Yeah, the rigid dinosaur grid of today. We use electricity for our lights and appliances, but we still use natural gas to heat our homes, and we still burn gasoline to drive our cars.
So the sectors are totally isolated. There's minimal electrification in other areas.
Right. And in that current siloed system, the peak hourly demand for electricity in the Danish model hovers around 7,900 megawatts.
Okay, 7,900. But that grid is on its way out. The study then models the second arena, the climate-neutral system of the future.
This is where it gets really interesting.
Yeah, because in this reality, heating, industry, and transport are all electrified. And because of that massive consolidation, the overall electricity demand jumps by a factor of 2.5 compared to today.
Which sounds like an absolute nightmare for grid operator.
Right. I mean, that was my immediate thought reading this. Wait, if the demand is 2.5 times higher in the future system, wouldn't that make everything vastly more expensive and difficult to balance?
It seems highly intuitive to assume that, yeah, more demand equals higher costs and more instability.
But they flip that, don't they?
Completely upside down. And they do it through a concept called sector coupling. You'll also hear it referred to as the power to X economy.
Let's break down the mechanics of sector coupling, because I feel like this is the magic trick of the whole paper.
It really is. See, in our current siloed system, electricity demand is incredibly rigid. When someone turns on their television, the power plant has to respond instantly.
Right, there's no delay.
But in the sector-coupled system, a massive portion of that new demand from heating and transport is inherently flexible. It doesn't need to happen the millisecond you plug it in.
Ah, okay. The classic example of this is smart charging EVs.
Right.
Vehicle to grid or V2G.
Exactly. You plug your car in at 6 p.m. after work, but you don't actually need the battery full until you leave for work at 7 a.m. the next morning.
So your car basically becomes a roaming battery pack for the grid.
Yeah. The intelligent system can choose to delay charging your car until 2 a.m. when the wind is howling offshore and electricity is virtually free.
Or what if there's a sudden lull in the wind at 8 p.m. when everyone is cooking dinner?
Then the grid can actually pull a tiny bit of power out of your car battery to stabilize the network, and they compensate you for it.
That's wild. The study also leans heavily into large-scale district heating to provide this flexibility, right?
Yes. Heating is a fantastic thermal battery. A sector-coupled system uses these massive district heat pumps.
How does that help balance the grid, though?
Well, imagine solar and wind are overproducing on a sunny, breezy afternoon. The system cranks up those heat pumps and stores the thermal energy in gigantic, highly insulated water tanks.
Oh, so instead of a chemical battery, you just have a giant thermos.
Exactly.
Yeah.
And storing hot water is magnitudes cheaper than storing electricity in a chemical lithium-ion battery.
So then later that night when the sun goes down and the wind stops.
The grid simply turns the heat pumps off. The homes stay perfectly warm by drawing from the hot water tanks, and the electrical grid sheds a massive load.
Wow. And we also have to talk about the X in power to X, which is electrolyzers making hydrogen.
Right. Splitting water into hydrogen and oxygen requires immense amounts of electrical power. They are heavy industrial loads.
But they're flexible.
Super flexible. Their superpower is that they can be ramped up or powered down in a fraction of a second. So they act as giant industrial shock absorbers.
So when renewable energy is just flooding the grid, you run the electrolyzers at maximum capacity.
Yeah, and you store that hydrogen gas in massive underground salt caverns.
Okay, so by coupling all these sectors together, that terrifying 2.5 times increase in demand actually becomes the grid's greatest asset.
You nailed it. It creates a vast reservoir of cheap flexibility that can effortlessly soak up all the unpredictable surges from solar panels and wind turbines.
All right, so we have the two arenas set, the rigid grid of today and the integrated grid of tomorrow. Now, what are the actual baseline costs being plugged into this simulation?
So they pulled their baseline data from the International Energy Agency, specifically the World Energy Outlook reports from 2023 and 2024.
And here's where it gets really interesting regarding nuclear power. The IEA assumes that by 2050, the capital cost for building nuclear will be around $4,500 per kilowatt.
Right, and that projection is heavily reliant on the assumption of what they call nth-of-a-kind cost reductions.
Meaning what exactly?
Meaning the economic models assume that eventually we'll stop building bespoke nuclear plants and start mass producing them on an assembly line.
Driving the price down through economies of scale.
Exactly. But this study provides a pretty harsh reality check on that theoretical assumption.
Yeah, they point out a glaring historical contradiction here, because nuclear costs have historically increased, not decreased.
Yeah, for over 5 decades. We don't build reactors on an assembly line. We build them like custom, hyper-complex cathedrals.
And the study cites recent European megaprojects to prove this, like Hinkley Point in the UK, Flamanville in France, Olkiluoto in Finland.
Right, and in almost all of those recent cases, the final price tags ended up roughly doubling their initial estimates.
Wow.
And the construction timelines stretched out for over a decade. It's mostly due to a loss of specialized supply chain expertise, combined with, constantly evolving safety regulations after Fukushima.
Right. Every new safety mandate requires retrofitting designs mid-construction, which just burns through capital.
Exactly. And because these projects routinely take 9 to 12 years to build, they carry immense financial project risk.
Which brings us to the discount rate.
Yes. The time value of money is brutal for nuclear power. To account for this immense project risk, the IEA applies an 8% discount rate for nuclear.
Versus just 5% for renewables.
Right, because a solar farm can be constructed and generating revenue in a matter of months.
Let's explore why that 8% matters so much. Because if you lock up $10 billion to build a nuclear plant, and it takes 12 years before the reactor splits a single atom
and generates a single dollar of revenue.
Yeah, the interest on that locked up capital just compounds relentlessly.
The financing costs alone can eclipse the cost of the concrete and steel. So when this study applies that 8% discount rate, that optimistic $4,500 overnight cost balloons dramatically.
What does it reach?
The effective capital cost pushes to a staggering 10,000 to 11,200 euros per megawatt.
Okay, that is a colossal premium. But I want to push back on this a little bit on the operational side.
Sure.
We constantly hear the argument that nuclear is baseload power. It runs 247. It doesn't care if the wind is blowing. So why does this study add system integration costs to nuclear?
It's a great question.
Shouldn't its SLCOE just be its baseline LCOE since it doesn't need batteries?
Well, that is one of the most persistent myths in the entire energy debate. The idea that nuclear provides a perfect, 100% reliable baseload that requires zero grid support.
It doesn't.
No. The reality, based on global operational data, is that the average capacity factor for nuclear power worldwide is only about 80%.
Wait, really? So a fifth of the time, it's not producing power at all?
Exactly. Reactors have to go offline. They need weeks for complex refueling procedures,
Yeah.
rigorous scheduled maintenance, or, unexpected safety reviews.
Okay, but when it is on, it's constant, right?
Yes, and that's actually part of the problem. Nuclear power is fundamentally inflexible. Its physics and economics dictate that it wants to run at a constant flat output.
Ah, so it can't easily ramp its power up and down hour by hour to chase demand?
Right, like when everyone comes home at 6 p.m. and turns on their ovens, nuclear can't just spike to meet that. And worse, if a massive 1 gigawatt plant trips offline for maintenance, the grid operator has a huge hole to fill instantly.
So what do?
Because of that lack of flexibility, a grid relying heavily on large-scale nuclear actually requires roughly a 25% reserve capacity margin.
Like backup gas turbines.
Exactly. The system has to build and maintain an entire fleet of backup gas turbines just to cover the system when a reactor goes down. And all of that extra infrastructure adds heavily to the system integration costs of nuclear, driving its SLCOE way up.
Okay, we have the arenas, we have the costs. What happens when the simulation runs hour by hour for a year? The ultimate showdown. Let's look at round one, the electricity-only system. Today's grid.
The results are pretty brutal for variable renewables here.
Yeah, because in today's grid, the system costs for solar and wind are massive, right?
Astronomical. Without the smart EVs or the district heating to absorb the variability, the only way to keep the lights on during a windless night is to build vast arrays of chemical batteries.
Which are super expensive, so their SLCOE skyrockets.
Exactly. Now, nuclear system costs are actually lower here, though its base LCOE is still huge.
Round two is the massive twist, the climate-neutral system.
Yeah. In the integrated future system, the SLCOE of renewables absolutely plummets.
Why? Because the system doesn't need those expensive batteries anymore.
Right. It uses the cheap flexibility of heat pumps and hydrogen storage. The integrated system just absorbs the wild fluctuations effortlessly.
So after running all those hours, the algorithm identifies the least cost mix. And the winner is a combination heavily dominated by offshore wind.
Up to 84% in scenarios where biomass is restricted, complemented by solar PV.
And nuclear.
Nuclear simply cannot compete economically in any of the future scenarios. Even with optimistic cost reductions, its SLCOE remains substantially higher than a smart mix of wind and solar.
So what does this all mean? I kept trying to visualize this, and it's like having a high-energy working dog, like a border collie.
Okay, I like where this is going.
Right. In a tiny apartment, which is our electricity-only grid, it's chaotic and expensive to manage. You're buying crates, hiring dog walkers. It's a nightmare.
The system costs are unsustainable.
Exactly. But put that same dog on a massive farm, the climate-neutral, sector-coupled system, and suddenly its energy is perfectly utilized.
The dot hasn't changed, but the environment expanded to harness its nature. It perfectly captures the thesis of SLCOE.
Now, any good study anticipates the skeptics. What if the IEA's predictions for 2050 are totally wrong? They ran a sensitivity analysis, didn't they?
They did. Stress testing the math is vital. They asked, what if offshore wind costs jump 50% due to supply chain bottlenecks? What if electrolyzers get 50% more expensive?
Especially with recent inflation. They used higher Danish Energy Agency cost adjustments, right?
Yeah, and if we connect this to the bigger picture, the results are incredibly robust. Even with artificially inflated capital costs for renewables, the structural finding remains identical.
The integrated renewable mix is still significantly cheaper than nuclear.
The hierarchy never flips. The system integration costs are just so inherently low for renewables in that flexible environment.
What about the other way? What if battery costs drop by another 50% due to some breakthrough?
That helps the electricity-only system a lot, but it barely changes the climate-neutral system.
Why wouldn't it use the cheaper batteries?
Because it's already using better, cheaper flexibility options. Storing hot water or hydrogen in salt caverns will always be fundamentally cheaper than manufacturing complex chemical batteries. Sector coupling makes massive battery banks structurally obsolete for long-term balancing.
Wow. So to summarize this for you listening, the next time you hear arguments about which energy source is cheapest, remember that you can't just look at the technology. You have to look at the system it lives in.
The true cost is entirely a function of the relationship between the generator and the network it feeds.
We have been unpacking the complex mechanics hidden within the research paper, SLCOE, System-Based LCOE, for comparing energy technologies in different systems. It completely alters how you view the energy transition.
It really does. And it leaves us with a final question to mull over. If the true cost and efficiency of our future energy depends entirely on how interconnected our society's infrastructure is, are we focusing too much of our public debate on inventing slightly better solar panels and reactors?
And not nearly enough on how we redesign our cities, our heating, and our transport to actually talk to each other.
Exactly. Because the cheapest future isn't unlocked by better hardware. It's unlocked by building a smarter, wider farm for all that wild energy to run on.
A perfect thought to end on. Thanks for joining us on this deep dive, and we'll catch you next time.